So now, for our lunch entertainment, uh, Sonja Sachs is going to do a presentation on the health risk assessment. And we purposefully didn't do a session on that, and there was a reason for that. It's because all the stuff we talked about this morning and yesterday afternoon feed into the risk assessment. So we just thought an overview of the risk assessment would be helpful, and because of time constraints, we're not going to take questions from the general audience or from the web folks. We're just going to take questions from the policy people. So thanks.
Hi, everyone. I'm not going to sing and dance, but I am going to talk about risk assessment a little bit. And I think, well, first of all, just to set up, I'm Sonja Sachs. I work at Gradient. I've been working on NACS issues for about 6 or 7 years together with Julie Goodman. And a lot of our work has been in the context of regulatory commentary and evaluating all of the EPA documents, including the risk assessments. And this work has been done for a variety of trade organizations, the American Petroleum Institute, for example, and other trade organizations. So, like I said, this is going to be a very quick, short overview of the ozone risk assessment. I'll try to cover as much as I can in this limited time, but really highlighting some of the strengths and limitations of the risk assessment. And I should preface also by saying that this is a piece of information that the administrator uses as part of the decision-making for setting the NAC. So it is a fairly important part of it. But we've laid the groundwork with all the health effects science. That science obviously feeds into the risk assessment. So that helps a lot. We've talked a lot about the controlled exposure studies. That's one piece of it, the lung function decrements. We've now talked a lot about the epidemiology studies, and that also lays the groundwork for the risk assessment. So I have control. All right, so what did EPA do? They conducted actually 3 different assessments. One was purely an exposure assessment, and this was evaluating exposures for particular subgroups, what EPA called at-risk individuals. These are children, these are asthmatic children, they're asthmatic adults. And they evaluated the percentage of these groups of individuals that exceeded certain exposure benchmarks. And these exposure benchmarks were 60 ppb, 70 ppb, and 80 ppb. So in addition to the exposure assessment, they did 2 separate risk assessments. One risk assessment was on determining lung function decrements associated with exposures. And what feeds into this, what the basis for this risk assessment was the controlled exposure studies. So these are the FEV1 decrements that we talked about yesterday. The other risk assessment that EPA conducted was a mortality and morbidity risk assessment. And the basis of this risk assessment was the epidemiology studies that we discussed today. So first I'm going to talk about the exposure and lung function risk assessment. To do this assessment, EPA used the air pollution exposure model, or the APEX model. Now this is an exposure model, but it also was integrated with a risk piece to calculate the FEV1 decrements. The exposure model seeks to look at people's personal exposures. So the exposures that someone would experience in their everyday life, going through different microenvironments. So basically the model generates for simulated, so these are simulated people, it generates a year-long time activity pattern for each of the modeled individuals, and this time activity patterns are composed of exposure events. It's based on geographic location of that person determines their ambient exposure, the microenvironment, that is their home or their work or how much time they spend outdoors, will determine their actual exposure at any given time. And then it also has a way to determine activity levels in each of these microenvironments to get a sense of their breathing rate or their ventilation. Together with the exposure information, the ventilation information, then the model can calculate what the risk is that that individual would experience a lung function decrement. So this is just a quick overview of some of the major groups of inputs that go into the model. So there's the exposure estimates, there's the data from the controlled exposure studies, there's physiological parameters, there's ventilation parameters, exercise and duration, and all of this feeds into calculating the FEV1 decrements. Of course, the picture is not so simple. So this is a very busy figure, and I'm not going to go through it in detail, but it's just to give you an idea that this is a very complicated model. There's a lot that goes into it. There's a lot of different inputs. All the boxes in blue are the actual inputs that go into the APEX model. All of these inputs are associated with a certain amount of uncertainty. So if you can imagine really trying to quantify what the uncertainty is for that final little box at the top, which is your result, it's quite a daunting task. So let me talk about then, just in general, what are some of the strengths and the limitations of the APEX model. So some of the strengths are that it is a really nice, it's a very complex model, and it really tries to bring in a lot of different important parameters to quantify these risks. So it's time activity, it's the physiological parameters of ventilation, and importantly, they really try to get at what is a person's exposure rather than using an ambient monitor as the exposure metric. And this is, of course, because it's tied to the controlled exposure study data, this is the most relevant exposure that you need, because in a controlled setting, you are exposing them directly to a certain ozone concentration. Now, some of the limitations, and I just put together a few. The time activity information, for example, that goes into the model is quite dated. So it's from the 80s and 90s. It's very likely that information has changed over time, that our time activity patterns have changed. In particular, children. I think, unfortunately, I don't think children are as active as they were in the 80s and 90s. So that's a very important limitation. Another thing that's not necessarily captured, at least in the EPA analysis, is averting behavior. We talked a little bit about the air quality index. People pay attention to the air quality index, and many times will change their behavior accordingly. So if someone has asthma, or if your child has asthma and it's a high ozone day, you may look at that and you may say, okay, I'm not going to let my kid, play outdoors today. I'm worried about their asthma, so I'm not going to. So that's, that could affect their exposure. There's also very limited data on children. And so what EPA had to do oftentimes was extrapolate data for adults to children. So that's an uncertainty. The EPA really, really focuses on children in presenting the risk assessment results. This is, a group that is of concern, obviously, to all of us, especially, if you have children. Of course, you'd be concerned, and EPA tends to highlight the results for children. So just briefly, so the exposure assessment, as I mentioned, EPA quantifies the percentage of these at-risk individuals, particularly children, that are exposed above certain benchmarks. They chose 60, 70, and 80 ppb as being the benchmarks of concern. they looked at different scenarios. So what is, I think, interesting about this risk assessment and a little bit different from what you may traditionally think of as risk assessment is this is a comparative risk assessment. So EPA looks at scenarios, they look at what the current ozone levels look like, and then they look at what the risks are for meeting the current standard and meeting alternative standards. Now, the current conditions are basically what's measured at the monitors in any given year. The meeting the current and alternative standards, this is all modeling. So this is another piece of the risk assessment that is, based on certain assumptions about what happens, to NOx levels, VOC levels, how much you have to reduce them to meet, either the current standard or alternative standards. So this is another piece of information that, has a fairly significant amount of uncertainty associated with it. But I'm not going to go into it because it's pretty complex and we don't have time. But I just want to show, this is straight out of the proposed rules. So some of the results from the exposure assessment. Now what EPA presents here is one or more exposures. So this is a single day when a child would have an exposure above either 70 ppb or 60 ppb over an 8-hour average in that day. So that's on the top. And what I have highlighted here is actually 2 or more exposures above 70 ppb on any given day. And what I want to show is EPA just shows the average, and this is an average across all of the different cities that they evaluated and across all the different years they evaluated. And these percentages, this is the percentage of the simulated population. They simulated 250,000 children. And the percentages, it was 0 to 0.1 on average would experience an exposure of greater than 70 ppb. So that's a pretty small number. Now, EPA does extrapolate these percentages for this simulated population to the overall population in the urban area that they evaluated. So that's the number that you see would correspond to that percentage. Now, the problem with that is that these simulated populations in the model, EPA doesn't really show whether they are representative of the full population of children in that city. So that can be problematic in trying to extrapolate those numbers. So in terms of the lung function risk assessment, EPA evaluated 15 cities, 2006 to 2010. And again, even though they did evaluate adults, they focused primarily on children. They looked at FEV1 decrements of greater than 10%, greater than 15%, and greater than 20%, and FEV1 decrements that occurred one day or 2 or more days. So one thing that's important here is that the NACS is based on an 8-hour average, but the APEX actually models exposures of less than an hour. And so the FEV1 decrement can actually happen, in an exposure period that's an hour or less. And then the other thing to note is that EPA didn't do any, they did some sensitivity analysis, but they didn't really try to quantify what the uncertainty was for the estimates that they provide. So just to give you an idea of what the results look like, this is a little hard to read, and I apologize because I just copied it straight out of the REA, the Risk and Exposure Assessment. So this gives you an idea of how variable the results were. So you can see a lot of variability across cities. So that's the x-axis are all the cities, and the y-axis gives you the percentage of the simulated population group that experienced one FEV1 decrement greater than 10%. So you can see, and the spread on the on the y-axis. So the vertical spread is actually the different years. So in different years, you'll get different percentages of children experiencing FEV1 decrements in this simulated population. And again, this is how EPA presents the results in the proposed rule. And similar to the exposure assessment results, but here we show the lung function decrements. I'm highlighting 2 or more FEV1 decrements. The administrator is really focused on 2 or more because, you would reasonably say that 1 FEV1 decrement of greater than 10% in a year or in an ozone season is probably not very relevant. But if you start to have 2 or more, then maybe that becomes a little more relevant. But again, we're looking at, in terms of, and the other, in the second column, you have the alternative standard scenarios. So these are scenarios where you're meeting a standard of 70, 65, and 60. So this is presenting the results, and this is an average range. Again, you have different cities, you have different years, so it's presenting a range of the percentage of the simulated population that would be experiencing these FEV1 decrements. And then again, EPA is extrapolating what that percentage would be in terms of equivalent children in any given area. You can see these numbers are huge. But again, how realistic is that extrapolation? And I think what's very important here is that we don't see what the results are for just achieving the current standard, that's 75 ppb. So what do the numbers look like when you're going from the current ozone conditions to actually attaining the current standard? And this is what I show here. And I got this idea from Tim. Thank you, Tim. I actually had this in a table, but I thought it would be more powerful to see it in a figure. And what you see here, this is actually the maximum percentage of children. So this is the worst city, the worst year, and this is the percentage of children with 1 or more FEV1 decrement greater than 10%. Again, 1 or more, if you only have 1, it's probably not very clinically significant. But I wanted to just kind of show you what is the worst case. And what you can see here, so you have 1, the light blue is 1, and actually the dark blue, you can see when it starts to go, for some reason EPA showed results for 6 or more, for some reason. So when they presented results in the proposed rule, it was 2 or more. But you can see how different the numbers look for 1 or more versus 6 or more. The light blue, but basically what this shows is that going from current conditions to just attaining the current standard, which is 75 ppb, that is the most significant drop, right, in the percentage of the simulated population that we're looking at. And you really get very marginal benefit from going from 75 ppb to 70 and 60 ppb. So again, I think this is very important because it's showing that just attaining the current standard will achieve these health benefits that we're looking at. But going further, you may get a bit more of a reduction, but it's pretty marginal. And I think another important point is that this is just looking at point estimates. There's no confidence bounds. We talked a lot about confidence bounds, about quantifying uncertainty. This doesn't show any of that. So are these statistically significant differences? That's the question. So one other thing that we tried to figure out is how realistic are these risks that we're looking at for these simulated groups, right? This is a model. It's doing the best it can, but it has limitations. So one of the things we looked at is how does the exposure assessment relate to the risk assessment? And we found quite a bit of a discrepancy, actually. knowing what we know from the controlled exposure studies, knowing that there shouldn't be a lot of risk, meaning FEV1 decrements, associated with exposures, certainly less, or for people that are exposed greater than 60 ppb, we found that the percentage of children that are exposed to concentrations greater than 60 ppb was so much less than the percentage of the kids that were actually experiencing FEV1 decrements. Now, part of this is because the APEX model is, the exposure assessment is based on an 8-hour average exposure, whereas the APEX model is considering exposures that are less than an hour. So you can have an FEV1 decrement with an exposure of ozone less than an hour. So that's part of this question. But it also, and I'll just show you kind of what the controlled exposure data look like. And what this highlights is, again, that there isn't a lot going on above 70 ppb in terms of FEV1 decrements. And again, I should qualify this by saying these are the group means. So these are not the individual data, which the APEX model is also considering the individual data. So these are the group means. But again, the idea is that there is some sort of threshold going on here, and that's not really reflected in the APEX model. Now, another issue with the APEX model, and we wanted to figure out, what do these kids look like that are being modeled in terms of some of the parameters that are contributing to potentially high ozone exposures and that are contributing to these FEV1 decrements. So this is a figure, this is for Los Angeles, it's for current ozone levels. So this is current ozone levels in 2006. And what this shows is these are just the kids that are experiencing FEV1 decrements greater than 10%. Oh. Okay. So one thing to note is, first of all, if you're just looking at the kids with greater than FEV1 decrements greater than 10%, it's the blue, so a lot more kids. And the red is greater than 15%. So we get a huge drop when we start to look at, a target decrement that's a little bit higher. But this is showing that on average, these kids are spending about 5 hours outdoors. And that's, I think that's a lot. and I think, if you recall what Sabina was showing in her analysis, I think that it was more around 2.6 hours on average for moderate exercise. Yeah, because so on this next slide is where we start talking about ventilation results. And again, these are children that are experiencing greater than 2 FEV1 decrements. The blue is 10%, and the red, again, is 15%. And here, again, I'm pointing to kind of the average here is around 20 liters per minute. And that is, a fairly moderate ventilation rate. So not only are these kids that are being modeled, they're spending a lot of time outdoors doing fairly, moderate to high levels of activity. And you can see it's a distribution. So once you start getting to the tails, it starts getting a little unrealistic, right? Because I'm not sure, unless you're looking at a super athlete, kid. And if I go back here, on the tail end of here, kids are spending, most of the day outdoors. And, you certainly wouldn't expect 24 hours a day, hopefully. So just to, summarize a little bit, the results are highlighting, effects in exercising children. These are, children that have very high ozone exposures. Risks are being observed below 60 ppb when you consider an 8-hour average, which is not necessarily consistent with the controlled exposure studies. EPA tends to highlight the results of, decrements of greater than 10% once or twice in an ozone season. Whether that's really clinically significant, we certainly had that debate yesterday. But it's very important that we consider these are models, and there's a lot of uncertainty, and the uncertainty, needs to be quantified to the best we can do, and it really hasn't been done, and I think it really needs to be done. And as I showed, the results don't seem to indicate that if we lower the standard further from the current standard, that you're really going to get substantial benefits that, are clearly statistically different from what you get from just attaining the current standard. So I'm going to switch gears to the risk assessment that's based on epidemiology studies. Now here we're talking about a completely different model. EPA used the Benefits Mapping and Analysis Program, or BENMAP model. They evaluated 12 cities and 2 years, and they also evaluated current conditions, just meeting the current standard and alternative standards. And I'm gonna talk mostly about, they did mortality, they did short-term mortality, they did morbidity endpoints, hospital admissions, emergency department visits for respiratory disease. I'm gonna focus just on the short-term mortality. And this risk assessment was based on the concentration response function from the Smith study that we talked about extensively, that wonderful heterogeneous figure that we talked about a lot. So this is a nice segue. Now, the risk estimates that they used for each city were the city-specific risk estimates, but they were the Bayesian adjusted concentration. So they were the shrunken, we talked about these shrunken estimates. You're shrinking the confidence bounds. And they did consider, they based their prime analysis on single pollutant assessments, but they also did some sensitivity analysis with concentration response functions that considered PM as a co-pollutant, but they did not consider a threshold. So those are some of the issues. And let me give you a little bit of an overview of BENMAP. So that, again, we have various inputs that go into the model. The air quality, either the current conditions, which are just based on the measured ambient monitors, or the modeled estimates for meeting the current standard or alternative standards. You have data on population and baseline health data. You have the concentration response functions that are coming from the Smith study, and what you get is your mortality, your incidence mortality or morbidity. Again, that was the simplified view. This is the more complex view. So you really have a lot more going into this. And each step of this process has a certain amount of uncertainty associated with it. Now, when EPA shows the results, they were not very striking. These look like, you're getting slight decreases with, on the x-axis, it's going from 75 ppb, 70, 65, 60 ppb. So this is reducing the standard, the ozone standard, and these are the mortality estimates. So you get a little bit of reduction, but not very compelling. And I should also mention that the administrator places a lot less weight on this particular risk assessment for a lot of the limitations that Julie talked about, the limitations of the EPI studies. And so So she didn't place a lot of weight on these risk results. But I think what's important here is that, again, EPA is showing point estimates here. What really should be seen is what these results look like with confidence bounds around them. And when you start putting confidence bounds, you start to notice that there isn't a lot of difference between going from, the current standard to alternative standards. When you consider those confidence bounds, you're not really seeing statistically significant changes for these scenarios. And I just wanted to show what things look like when you start, when you include PM in the model. Now, these are some cities where you can see that the confidence bounds actually don't straddle the null, a null finding or a no effect finding. But when you put PM in the model, suddenly, you don't get a significant mortality result. So just highlighting some of the issues with this risk assessment, and again, I think, the administrator was right in not placing a lot of weight on these results, which are not very compelling to begin with. But again, as we talked about, there's no, the causality is uncertain. There's no real mode of action that we can point to for ozone causing death. Also, the way that EPA did this analysis introduced a lot of uncertainty. Instead of using the urban area as defined in the epidemiology study, they used a broader area. So that introduces uncertainty. When EPA decided on the concentration response function that they were going to use, they used a Bayesian adjusted response function that was based on scaling it by the national estimate instead of a regional estimate. We talked a lot about heterogeneity. Because of that heterogeneity, it makes more sense to use a regional based estimate. Again, they didn't do any statistics, so I don't know. It was pretty clear to me that you're not going to see a lot of statistical difference between the risks for the current standard and alternative standards just based on the confidence intervals. But it would be nice to show that statistically, and EPA doesn't do that. And as I said, when you look at those confidence intervals, it really doesn't look like you're getting a difference. And just briefly, I wanted to touch on EPA also looked at long-term ozone exposure and particularly respiratory morbidity. Now, this analysis is even more uncertain than the short-term mortality because it's based on a single study that found a positive effect, and this is the Jarrett study. This study has limitations. These limitations are not captured in confidence intervals. As you can see in this graph, even though EPA asserts that there's no threshold, this graph clearly shows that there is a threshold. And Jarrett used a 1 hour averaging time. The threshold was 56 ppb for the 1 hour averaging time. If you make that equivalent to an 8 hour, which is the basis of the NAAQS, this threshold is well above the current level of the NAAQS. So when you consider this threshold in the risk assessment, your mortality risk essentially goes to almost zero because there's no effects at the lower ozone levels. So in conclusion, EPA did a fantastic job. This was a lot of work. The risk assessment, I would say, was very rigorous, but it has some serious limitations, and those limitations need to be discussed when discussing these risk results. Presenting point estimates are not useful. They're not useful in the absence of discussions about the uncertainty in these models. And as I noted, these models are very complex, and there's a lot of inputs that go into them, and there's a lot of uncertainty in each of those inputs. It's a daunting task to do an uncertainty analysis for this type of model, but it needs to be done. There were some indications that the risk estimates, particularly for the lung function, were maybe not overestimated, but certainly represent worst case scenarios. I mean, these are children that are spending a lot of time outdoors, engaged in very heavy exercise. And do we want to protect those children? Sure. But should a standard be set to a level that is just protective to those particular children? And when you do look at the results, it really is indicating that we are getting benefits from just meeting the current standard, and that any marginal benefits that we get from meeting alternative standards are probably not very significant. And so maybe we need to consider trying to meet the current standard before we start, moving the goalpost, as some people have described it as. So thank you very much. And I guess I will take questions from the policy group. Sorry, I went a little long.
You have questions from the policy panel?
You made the point about uncertainty, and I guess I'm just interested in the work involved in doing that. Why, presenting these kind of conclusions on the apex side, without the uncertainty analysis, seems a little puzzling to me. With respect, on the apex, I'm interested in just lining it up with Dr. Lang's, presentation.
Yeah.
I'm having a hard time seeing the, why the model is showing such, evidence of decrement, below 60 after 1 hour in light of Dr. Lang's presentation. I don't know.
Right.
If you can speak to those two things with respect to the apex, that would be helpful.
Yeah. Yeah, that and we've had discussions about that as well. As I mentioned, I mean, this is a very complex model. It's sampling from the time activity data that actually Sabina, looked at and used as well. But it's doing this random sampling, and it's in my mind, it is kind of oversampling these children that have, as we showed, are spending a lot of time outdoors, engaged in very heavy exercise, and I think that's what you're seeing. You're seeing these signals, and it's unclear whether it's really a realistic scenario. It may be, but it's unclear whether, how realistic that sampling is. It ties into the McDonald model that has a lot of different parameters. We know ventilation rate, and so assumptions that go into about ventilation rate in the model, the starting point, let alone, the distribution, is going to impact. I mean, all of the inputs, what Sabina did was, a simplified version. I mean, she's using the same data, but she's kind of simplifying it down. This model is very complicated, so it has a lot of inputs, and the assumptions that go into deciding what the starting point is for those inputs makes a big difference, and that's what we're seeing, I think. I don't know if I answered all of your questions.
I still have a question just on the uncertainty analysis, but then also with respect to the EPI side of it, given all the uncertainties that were discussed earlier, was it appropriate to move toward monetizing the cost of mortality avoided? That the agency did that, but just perspective on that, or maybe that's for a later panel, with respect to.
Yeah, I mean, that's going to, I think, be discussed.
It's just, it's all building on itself, because you have
I agree.
the concerns regarding the the EPI studies that you noted, and then we have the risk assessment. But at the end of the day, it's taking all of that information and, as somebody said, presenting a story.
Right.
And it all is linked, and I'm just trying to understand the strength and reasons kind of for moving along the chain when maybe it's more appropriate to
Yeah.
stop at some point.
Well, I think, I mean, I agree with you. I think that, you know, in as much as the EPI studies risk assessment is important is because it does feed into this, you know, the RIA, right? The regulatory impact assessment. And it's huge. I mean, when you start talking about mortality and monetizing mortality, you start to get really big numbers. And I think that
But they're built on this evidence that we've been looking at.
correct.
That's what that's my
Correct.
point. Okay.
But I think, you know, the issues of uncertainty and the limitations in the underlying studies often don't get discussed enough when developing these estimates. But yeah, go ahead.
I just want to add something about with a potential difference. I'm not sure that this is true of the apex, but I suspect it is. The ventilation rates and the duration rates, for example, that I showed in that table, they all have, what I showed was the mean and then the 90% and the 10% number. But if you, for example, were to use the maximum ventilation rate and the maximum time, then you would get a considerably higher dose than if you use the mean time. And it's not saying, so you're compounding you're compounding the tails. So you could certainly get a much higher dose if you multiply the tails together. Although I'm not sure that you actually have a person who's ventilating at the highest rate for the highest period of time. I'm not sure that that's an accurate assumption of what people are actually doing. So that can contribute to it.
You mentioned that the administrator is placing or has placed less weight on this type of analysis. So how is that manifested?
Well,
Or what did she say? Or how
well, I think
does that mean?
I think in discussing the results from the risk assessment from the epidemiology study, I mean, they're certainly in the proposed rule, but the administrator notes the limitations that Julie, you know, discussed in detail. The exposure measurement error, the heterogeneity in particular. So all of those issues limit, you know, how much weight you put on the assessment. And, you know, in reality, you know, as we discussed on the controlled exposure studies, we really believe that the administrator, you know, is placing the most weight on that information.
So I'm still unclear what that means. Is the proposal explicit and transparent about that? Is it weighted in some way?
I don't know.
Is it
Julie,
some
do you
good-
think it's very explicit? I was noting that the administrator places less weight on the risk assessment, particularly the EPI risk assessment. But is it very explicit? I'm not sure if it's, I mean, you think it is? Yeah. Yeah.
So I'm Ann Smith with NERA. The way that the question of weight is being handled in the proposed rule is entirely qualitative. It's just describing the evidence, trying to integrate it and saying there's less weight. But in the risk assessment, it gets 100% weight. The quantitative analysis of the numbers of FEV1 decrements as well as you know, morbidity and mortality events are entirely, you know, treated as if they're valid, 100% certain. And the uncertainty that Dr. Sachs was showing in the ranges for the epidemiological studies is only the statistical variance.
Yeah.
And there's no modeling uncertainty represented there.
Yeah. Yeah. Thanks, Ann.